Alrighty. So to talk about 5.3, which is proving trig identities, these are the last two questions on 5.2 where we were simplifying. It's really the same kind of process that we're doing today. The difference is going to be in kind of how the questions look. So instead of me giving you something to simplify and you get down to an answer that you're not sure what it's supposed to be. And also, just in case I didn't say this yesterday, on the assignment, which I don't think I did, on the assignment that was given yesterday, all of your answers, have to be in one term or one number. There is one question on there on the assignment that's two terms. You can't get it down to one term, but there's only one of them. I'm not going to tell you which one it is, but there still should be no fractions and only one of them that has two terms. Okay. So when we prove, instead of just me giving you something you have to simplify, I'm basically going to give you the question and the answer. So the question would look like this. So you know exactly where you're headed, and then you just have to make this look like this, which is kind of what we did. All right, so the process is kind of the same as yesterday. So let's look at 5.3. So if we're proving or verifying identities, so proving or verifying an identity means to show that both sides are the same. The show is the key word there. And those of you that are stubborn and haven't been doing what has been expected of you for probably years, like because you never want to show anything, are going to have more difficulty with this than the people that normally show most of their work. And the catch here is this too. If you're solving for x, like it's just a simple whatever and you solve for x, if you skip some steps, as long as you know what you're doing, you get it right, I don't care. I'll skip steps too. Sometimes on the notes, I don't skip as many because I don't want to lose you when you're looking down, you look back up, and you're like, where the heck did that come from? So I'll write some extra stuff, but all that's fine. When you're proving or you're showing stuff, you cannot skip steps. That means you're not actually showing it. Like your work is your answer. And the steps I'm writing here, they're not extra steps. It's everything you would have to do in the same kind of manner. So use your notes, okay? When you get stuck on things, that's why we take them, not so that we have something to do for 45 minutes every day. All right, so when we prove an identity, we simplify one side of the equation until it's equal to the other. So you have to choose which side you're going to work with. It's usually a pretty easy decision because here's the hint. The hint is work with the side that looks, well, that's an arrow that looks bad, looks more complicated. So looks is, it means it's kind of a matter of opinion. It's not necessarily more complicated. And if you pick, there's not a wrong side. So if you pick a different side than I would pick, doesn't mean that you're wrong. It just may be making it more difficult for you. So like if you look at number 1, if I'm supposed to make one side look like the other, well, I think we could all agree that the left-hand side looks more complicated. And so I have a way better chance of being able to substitute things in and do stuff with that than I do of trying to guess at what to put in legally on the right-hand side to make it look like the left. You with me? You kind of have more, there's something to work with. So we're going to work with this side, make it look like this side. Same basic premise as yesterday. I have to decide what to substitute in that's legal. And so when I look at this, I have a cosine squared, which when I have the squareds, I want to go say, okay, maybe I have something Pythagorean I could put in. I don't know that putting it in right there would really help much at this point. I don't have any fractions or anything, but I think since this is cosine squared and this is sine, maybe if I go ahead and make this into cosine or sine, that'll kind of help me get started. So I'm going to take cosecant and make it into 1 over sine times cosine squared theta plus sine theta equals cosecant theta. And it's an equation, you rewrite the whole thing every time. You get sloppy and only rewrite parts of it, I'm probably not going to look at any of it. Okay? So on the left there, when I multiply this is actually going to be one fraction, right? So I'm going to have a fraction plus something that's not, so I'm going to combine them. My common denominator would be sine theta. And then the numerator, the left part would be cosine squared theta. this would have to be multiplied by sine over sine. So we'd get plus sine squared theta equals cosecant theta. Everybody good so far? Now remember, I'm only working with one side, so that cosecant, he just follows along the whole time. I don't get to mess with that at all. So I'm only messing with the left-hand side. Who wants to tell me what I can put in for cosine squared plus sine squared? What? 1. Vanessa. Thank you, Vanessa. Vanessa says we can put in 1. So I'm going to have 1 over sine theta equals cosecant theta. And then I know that 1 over sine is cosecant theta. And I'm done. And I knew that this was going to be my final step no matter what. Now, as you're doing these, when you get here and you think, okay, I know that's going to be 1. And oh, look, that'll give me 1 over sine, which has to be cosecant. Like, you might figure out a few steps at a time, but you don't get to jump from here to here. Because the proof, it's your work that you're showing one little thing at a time. So you have to write this to get to here. Okay? Any questions at this point? All right. So let's look at number 2. So if you look at number 2, and we're trying to decide which one is more complicated or whatever. I mean, they both have like 2 different little terms in them. But most of the time, you want to work with the fraction because it's usually easier to get stuff out of a fraction than it is to know what to do with the other side to get it into a fraction, okay? But again, not necessarily wrong, doesn't mean you couldn't get there. So we're going to work with the left-hand side, make it look like this side, okay? So that means that this sine squared y, who wants to tell me what I can put in for sine squared y? Anybody? So I look at my Pythagorean identities. What could I put in for sine squared? Close. I think I heard somebody else say something. Look at it again. You're saying it backwards. Anybody? Look at your Pythagorean identities. What is sine squared equal? 1 minus. Thank you very much. Do you see why it's the other way around? Okay, very good. So I've got 1, this makes this 1 minus cosine squared y, that comes straight from your identities, over cosine y equals, and I rewrite the right-hand side, secant y minus cosine y. And remember, y'all can talk to me too. So I'm still working with the left-hand side. Now here's what you don't want to do. You don't want to look at that and go, oh, 1 minus cosine squared. I can substitute in sine squared, because then you're just going in circles. And that happens sometimes when you're trying to get common denominators of fractions too. So think about why you just did it so you don't undo it. So I don't want to substitute anything in the numerator. I don't really have anything to substitute in for cosine. So what do you think we could do here? It's a strategy we used yesterday a couple times. What? Split it. Yes, I can split the fraction. And that's the one that doesn't necessarily come, to mind like, oh, that's what I'm going to do, but that's going to be very handy in these. So this is going to be 1 over cosine y minus cosine squared y over cosine y. And then I rewrite secant y minus cosine y. Everybody good so far? All right, so then 1 over cosine, that is secant. Cosine squared over cosine is cosine y, and that equals secant y minus cosine y, and we're done. Make sure you're not leaving off your y's, x's, thetas, alphas, whatever they are. I don't always say them when I'm saying it because I have to say so much, but they absolutely have to be part of what you're writing, or it doesn't make any sense. Any questions at all at this point? Okay, so let's look at number 3. Now, number 3, when I look at it, there's 2 general ways to start this that jump out at me. There's probably more than 2 ways to work it, but 2 specific ways that I kind of see at first. Obviously, I think you see we want to work with the right-hand side to make it look like the left. So as I'm going to take you through number 3 a specific way. Along the way, if you're thinking, well, couldn't I have done this, or wouldn't it have been easier to do this? Just hold on to that thought for a minute, because the answer is most likely yes, and we have another one very similar to this that we're going to work the other way, okay? So I just kind of want you to see it both ways. So I'm going to rewrite the left side. So this is cosine squared alpha equals, when I look at the right-hand side algebraically, I have a GCF. So I'm going to factor out my GCF, which is sine squared alpha times cosecant squared alpha minus 1. Okay. Rewrite my left-hand side again. And then I have two different parts of Pythagorean identities. I could substitute them both, but remember, you don't really want to do two things at once because you may not want to actually do the other thing. And most likely you would want to get rid of the two-term one instead of the one-term one. Not always a guarantee, but it would simplify it a little bit better. So I'm going to leave the sine squared. And then when I look at my reference chart, I have cosecant squared minus 1. Who wants to tell me what I could substitute for that? Somebody besides Vanessa, go ahead. Cotangent squared, good. I don't want to squash y'all because I appreciate you participating. I want to make some other people talk too. So, all right, so cotangent squared alpha. So like I said, I could, for sine squared, I could substitute 1 minus, or cosine squared, but I don't know that that would really do anything for me. I know that cotangent is cosine over sine, so I think I'm going to go with that. So this gives me cosine squared alpha equals sine squared alpha times cosine squared alpha over sine squared alpha. So that's nice because then these cancel out and I get cosine squared alpha equals cosine squared alpha. What questions do you have? Anything? Okay. All right, so number 4, I think it's obvious we want to work with the left-hand side because it's really crazy looking, and we'll make it look like this side. You have two basic ways you could start this. We could start by distributing tangent first and then worrying about getting common denominators, or we could get a common denominator first and then distribute. And it really doesn't matter. We'll do it whichever way the first person that's willing to tell me which way to do, that's what we'll do. Somebody give me something. What do we want to do? Want to distribute or get a common denominator? Okay, so we're going to distribute, so thank you. Give you a sticker too for saying something. So we're going to distribute first because it's just, we get the same answer in the end. The steps just look a little different, doesn't really matter. Now, did you just pick one or did you think through it? Okay, that's fine. So I'm going to, when I do that, the tangents are going to cancel, so that leaves me with secant x minus tangent times tangent is tangent squared x over secant x. And honestly, if you can see two different ways, sometimes if you can't reason through either one of them, because it really doesn't matter here, just pick one and just go with it and see what happens. That equals cosine x. All right, so I still have two terms. I'm not avoiding the common denominator thing, I just didn't do it first. So I'm going to need to get, my common denominator will be secant x. So that first term will be secant squared x. And then that second term will just be tangent squared x. That equals cosine x. Okay. So then I've got some squareds. I go look at my Pythagorean identities. And is there something I could substitute for secant squared minus tangent squared? What would it be? 1. Good. 1. Very good. So secant squared minus tangent squared is 1. So I get 1 over secant x equals cosine x. And then I know that 1 over secant x is cosine x. That equals cosine x. And we are done. What questions do we have? Are we good? All right. Yes. Number 5. Okay, so number 5 and number 3 are very similar in the way that they are set up. Because if you look at number 5, I think, we're going to work with this side and make it look like this side. I have two terms again with a GCF. Could totally factor it out and do it in the same manner as we did number 3. However, the other way we could have done number 3 and what we could do in number 5 is look at this cosecant times sine squared. So how are cosecant and sine related to each other? They're what? Reciprocals, okay? They are reciprocals. So that means when I multiply them together, what do I get? What? 1. Who said that? Okay. 1. So when I multiply them together, because I can't tell when your mouths are moving with your masks, you might have to speak and raise your hand at the same time so I can figure it out. So when I multiply these two together, since they're reciprocals and they're both squared, I'm going to get 1. So that makes this cotangent squared theta equals, this is still cosecant squared theta, and then this is going to be minus 1. Okay. So then I'm going to rewrite my left-hand side, and then I'm going to look at my Pythagorean identities. Cosecant squared minus 1, what can I substitute for that? Cotangent squared. Very good. And then I'm done. So if you look at the steps on the 2, okay, yeah, number 5 was way shorter. And maybe you would think number 5's easier. The one that's easier is the one that makes the most sense to you at the time. It won't always be the shortest one, but it won't always be the longest one. So yes, you want to kind of think through it before you start, but don't spend more time trying to figure out what's the easiest way. See something that makes sense to you and go with it. And if you get stuck on one, like you're halfway through and you're like, I don't know what else to do, or I'm going in circles or whatever, leave it alone, go on to the next one, and then come back to it. But when you come back to it, don't come back to the same place you're already stuck on. Start completely over, and maybe you'll see something different, okay? And then just know that it gets better, and hopefully is this making a little bit more sense than it was yesterday? And hopefully, I mean, that's why we're doing so many of them, so you can see the different things that are happening, okay? All right, number 6. We definitely need to use our chart on number 6. Because remember, when we have a negative angle, it's not just a substitute. We're not substituting. We're not factoring it out. So when I have this, I'm going to work with this side, make it look like this side. Tangent of negative u. So I look on here at my even and odd identities. Okay? Oh, looking right through that. Then tangent of negative theta is negative tangent theta. So this becomes negative tangent u. Then sine of negative u. So sine of negative theta is negative sine u. Plus cosine of negative u. All right, well, cosine of negative theta is cosine theta, so this is just cosine u, and all that equals secant u. Okay? Everybody okay with where everything came from? All righty. So on the left-hand side, since that's the one I'm working with, when I multiply these two together, negative times negative is a positive, so I know this will be positive. I know tangent is sine over cosine, so when I multiply it by this, I'm going to get sine squared u over cosine u. Then plus cosine u equals secant u. Left-hand side, I'm going to have to get a common denominator. That common denominator is cosine u. So that first term, sine squared u, plus, this will be multiplied by cosine over cosine. So that's cosine squared u. All that equals secant u. Still working with the left-hand side. Sine squared plus cosine squared. I look at my Pythagorean identities. What can I substitute in the numerator? 1. Okay, 1. All right, so that means that sine squared plus cosine squared is 1. So 1 over cosine u equals secant u. And then 1 over cosine is secant. So secant u equals secant u. What questions do you have? Good. You could. Well, not really, because then you're going to end up with cosine squared of negative u plus cosine squared of u. Does that make sense? Well, actually, yeah, and then this would be negative down here. You with me? Like all these, well, you would have to switch it here. You couldn't do it at the very end. You'd have to do this here so you can actually put those together. Because you don't, cosine squared of negative u is not on there. That's not something you can replace. Does that make sense? Okay. I mean, that's a good point. We didn't have to do it right then, but you do have to do it before the very end. Okie dokie. Number 7. Maybe when this decides to cooperate. There we go. Okay, so I think we're going to work with the right-hand side, make it look like the left-hand side. So I'm going to rewrite 1 plus sine squared theta. Now, remember, the majority of the time, you're going to change one thing at a time, because if we change more than one thing, we may be missing an opportunity to reduce or whatever. And when you have a fraction, if it has more than one term in the denominator, that's usually what you want to fix first. It's nice if the denominator is just one term. So I'm going to leave my numerator alone for a minute. And then I have in the denominator 1 plus cotangent squared. So I'm going to look at this. And somebody that hasn't answered anything yet, what can I substitute for 1 plus cotangent squared? Who was that? Who said that? You have to point at her because she won't raise her hand. Okay, thank you. Yes, you're right. Cosecant squared. It's okay to be right and give an answer. It is cosecant squared theta. All right, so I'm going to rewrite the left-hand side. Now, on the right-hand side, I could substitute something for 1 plus cosecant squared theta, but it wouldn't just be cotangent squared theta. So look at your chart and make sure you understand why I can't just put cotangent squared in the numerator, because there's a different signage thing there. So I could substitute something in there, but I don't know that I want to do that. Maybe I would need to do that if these didn't match, but since these match, I can't just cancel them out. But somebody that hasn't answered something, what could I do? What's a strategy that we've used? Split the fraction. Did you say that again? Oh, very good. Split the fraction. So I can split it and make it into 1 over cosecant squared theta plus cosecant squared theta over cosecant squared theta. All right. Rewrite my left-hand side again. 1 plus sine squared theta equals, well, 1 over cosecant squared is sine squared, and then cosecant squared over cosecant squared is 1. So I think at this point we would all agree that the two sides have an equivalent value. They actually have an equivalent value all along the way. It's just not as obvious until we get right here. But we're not finished, and we can't skip this step to get to the last one either. So hopefully, in geometry, you should have done some algebraic proof. And the whole point of algebraic proof is to make you understand that everything in math that you do has rules, properties, theorems, postulates, definitions that allow you to do things that are math legal. We just don't always focus on what those are when we do them. And so one of the things, like let's say for instance I had 10 equals 5x. So most of you would probably put 2 equals x, which is right. I would put x equals 2 because, like I've said before, it was drilled into my brain growing up that the variable has to be on the left, which is not true, but I still just do it out of habit. And I can make that happen, but it's not legal for me to just jump to that step if I'm actually having to justify every step. I mean, it's fine because we skip steps when we solve anyway. But to get from here to here, I have to say, well, here I would actually divide by 5 on both sides. That gives me 2 equals x. And then there's a property that allows me to switch them, which is the commutative property. Or actually, this is the symmetric property. But when you do it just on one side, like we want to switch this is actually the commutative property. It doesn't matter if you know the words. I might even be saying the wrong ones, and I have a math degree, because it really doesn't matter. But there's a property that exists. So in order to actually make these identical, I have one more step. And luckily, we don't have to actually justify with those properties, just know that they exist right now. And then now I am done. It may seem absolutely ridiculous that you have to do that and that you can't skip this step to get here, but that's what proof is. You have to have every single step-by-step thing, okay? And that probably won't happen that often because a lot of times we just have one term left anyway, but we good? Okay. What happened? Oh, all right, so number 8. The right-hand side looks way worse than the left-hand side. I think we would agree on that as well. So I'm going to rewrite the left. Sine u plus cosine u equals. And then I'm going to kind of break one of the rules. It's not really a rule, but like a strategy that I've said over and over again already, which is we're only going to do one thing at a time. Every now and then it's okay to do more than one thing at a time if you kind of have a good reason for it. So when I look at the right-hand side, okay, I already have one fraction. I really don't think splitting it is going to help me because the denominator is yucky. There's nothing Pythagorean that I can substitute in. So really the only thing that I see that I can actually do would be my reciprocals and my quotients, right? And so, and I would want to, if I had to pick, I'd want to work with the denominator first. So I could just go through and do all the denominator, and then I could go through and do all the numerator. But by looking at what I have, if I'm going to make this into sine and cosine, I'm pretty confident this is going to have to be sine and cosine at some point as well. Make sense? So because I've kind of thought about that, I think I'm just going to go ahead and I can take care of the numerator and the denominator like at the same time. It'll save us some steps. So I'm going to go ahead and make all of these into versions of sine and cosine. Secant, I'm going to make 1 over cosine. Cosecant is 1 over sine. Tangent, sine over cosine, plus cotangent, which is cosine over sine. So I've got fractions and fractions, which shouldn't look as scary as they used to you, hopefully. But if you can't keep your work in an organized fashion and you can't read your own stuff, you're going to have a difficult time. And if I can't read your stuff, I might just give up. I mean, there's only so much I can do. It gives me a headache. Here, even though I have fractions and fractions, I absolutely positively would not multiply by the reciprocal here. Because that would, unless I have one fraction in the numerator and one fraction in the denominator, otherwise this would be a nightmare. And if you did it right now and you didn't think it was a nightmare, you're not doing it right. So it doesn't matter anyway. But you don't want to do it here. We need to simplify before we can get to that point. So I'm going to rewrite the left-hand side. Plus cosine u. So over here, I need to combine the fractions in the numerator and the denominator. So the common denominator of the numerator would be cosine u, sine u. So then the numerator of the numerator would end up being sine u plus cosine u. Then I need a common denominator in the denominator, and that would be cosine u, sine u. Then this first term would be sine squared u plus, and then the other one, cosine squared u. So I still have, so now I do have one fraction in each one, but again, before I worry about multiplying and stuff, I want to simplify it as much as I can. So sine u plus cosine u. I can't simplify the numerator anymore. Like I can't cancel these signs out. That would be totally illegal. So I'm just going to rewrite my numerator as sine u plus cosine u over cosine u, sine u. And don't worry, I've never had a student whose hand fell off because they were writing all this. You'll survive. And then in the denominator, sine squared plus cosine squared, y'all just tell me, what is that? 1. It's 1. We should know that by now. So that is 1 over cosine u sine u. So now I have a fraction in the numerator and denominator. They're both condensed to 1 and as simplified as I can get them at this point. So I'm going to rewrite the left-hand side again. Sine u plus cosine u. And now I'm going to actually divide these by multiplying by the reciprocal. So this will give me sine u plus cosine u over cosine u sine u times the reciprocal of the denominator, which is cosine u sine u over 1. And then all this horrendous looking stuff cleans up really nicely because these are going to cancel out, and that's where I get sine u plus cosine u equals sine u plus cosine u. And I'm done. What questions do you have? Somebody's got to have something. Okay. All right, number 9. So number 9 is it's kind of a tricky one. And, which side is more complicated? Well, that's kind of a matter of opinion as well, except I usually go for the fraction one. The left-hand side over here, if I was to actually square this out, would this be cosine squared plus cotangent squared? Algebraic, no. The answer is no, because that sends you to math jail, right? That's like this right here. I thought x plus 3 squared was x squared plus 9, because it's not. You don't get to just square them both. You would have to actually FOIL it out, but we're not going to do that, because we're going to work with the right-hand side, and we're going to leave this alone. So we're going to make it look like this. We're going to start with this. So I'm going to rewrite cosecant A plus cotangent A squared. So we're going to have to do something kind of creative with the right-hand side. Whereas honestly, if we work with the left-hand side, we wouldn't have to be this creative. But working with the left-hand side is super duper yucky. So it's almost better to have to be creative. And again, I know you don't always know that going into it, but you just have to trust me at this point. The creative part that you'll have to do here, the good thing is that they'll all kind of look like this, and if you're actually using your notes when you're doing your stuff, you can probably kind of figure it out here. So when I look at the right-hand side, nothing jumps out at me as what I could substitute in or what I could do. I don't think I want to split that fraction. There's nothing squared. I could put in reciprocals, but I don't know how that would help me, and so I'm kind of stuck. So I'm going to use what's called the conjugate, which at this point you usually should know what that is. But from what I've gotten today, I have a feeling that might be what was supposed to have been taught during quarantine last year, and maybe that's why nobody knows what those words mean. I don't know. But you're first introduced to conjugate in Algebra 2. So like if we're trying to rationalize the denominator of a radical, and you know what to do if the denominator is just square root of 3. But if it's 2 plus the square root of 3, you have to multiply by the conjugate, which is 2 minus the square root of 3. Now, this isn't a square root, but I would still use the conjugate idea here. And I can multiply any fraction by a value of 1, and that's totally legal. Like, I don't get to make stuff up and just throw in whatever I want. But the denominator here is 1 minus cosine, so its conjugate would be 1 plus cosine. So if I want this to be legal and not change the value, this has to have a value of 1, so the numerator would have to be 1 plus cosine A also. Right? So then the numerator is going to give me 1 plus cosine A quantity squared, because there's 2 of them. Right? The denominator, when I multiply them, what's that situation called? Come on, guys. You know this. No one say it. Somebody say it. 1 minus cosine times 1 plus cosine? What's that called? We did it yesterday. Shut up, Al. Somebody knows it. Yes, thank you. Who was that? Charisma. Thank you, girl. All right. Difference of squares, which means on that one, instead of me writing it out as these two things being multiplied, I'm going to go ahead and do that, and that is 1 minus cosine squared A. Difference of squares. Recognize them because they're easy and you can use it nicely. So now I'm going to rewrite the left-hand side, cosecant A plus cotangent A squared. Now on the right-hand side, I'm not going to multiply out the numerator because, I mean, maybe I'm going to need to, but I think I can do something with the denominator first. But one of the reasons I think maybe I won't need to is because the left-hand side isn't squared out. So I don't think I want to multiply that out. Maybe I'll need to, but we'll just kind of wait on that and see what happens. So 1 plus cosine A quantity squared, we're going to leave that up there. The denominator, though, I've got 1 minus cosine squared. So I look at my Pythagorean identities, and if I have 1 minus cosine squared, what's that going to be? Somebody. Don't look at me, look at your reference chart. Sine squared, yes, who said that? Okay, sine squared, yes, ma'am. So this is just going to be sine squared A down here. Okay, so I have the numerator is squared, the denominator is squared. And basically that's how you square a fraction also, right? So like if I said we have 3/4 squared, isn't that the same as 3 squared over 4 squared? It's the same thing, right? This is the form we're in right now, squared over squared. So I'm going to go backwards and make it into just one fraction squared. So I'm going to rewrite the left-hand side again. Plus cotangent A squared equals, and then I'm going to have 1 plus cosine A over sine A, and the whole thing is squared. Look at it for a second and make sure you understand why it's the same thing, just kind of in a different form. We usually go from this step to this step, but it's legal to go from this step to this step as well. Okay? So now, let me rewrite the left-hand side again. Cosecant A plus cotangent A squared. So what do you think would be the next thing we would do here? Split it. Yes, so I'm going to split the fraction. I'm going to get 1 over sine A plus cosine A over sine A, quantity squared. Rewrite the left-hand side. And then that leaves me with 1 over sine A is cosecant A. Cosine over sine is cotangent A. And they match. So that one's a tricky one. You have to think outside the box a little bit more. They're not all that crazy bad, but I think there's one on your assignment, but it kind of models that closely. So like I said, if you're using your notes, then hopefully you can kind of figure out what to do with that, and you can get through it. It's doable. Okay. We all good so far? Yeah. Yeah, and I've done it both ways, and you know, sometimes like maybe I should do it the other way, but then it's real yucky, and I don't know. But all right, number 10. I think we're going to work with the left-hand side, get it to the right-hand side. I'm going to get a common denominator. So my common denominator will be 1 minus cosine y times sine y. The numerator, the first term will be sine squared y plus, and then this will be 1 minus cosine y squared. That's equal to 2 cosecant y. My denominator is still 1 minus cosine y times sine y. And I'll go ahead and do the 2 cosecant y over here. So I didn't distribute this. Maybe I'm going to need to, but I feel like, and I can't like cancel one of these out or anything because of the way the terms are, but I'm going to need to actually square this. And I don't get to just square both of them. You have to be able to actually know what your rules are for that. So sine squared y plus, this becomes 1 minus 2 cosine y plus cosine squared y. Why? Because algebra, and I don't have time to reteach that for the 5 millionth time. So now when I look at what to do with this, I'm looking at my numerator. There's no like terms I can combine. However, I do have sine squared y plus cosine squared y, and we all know by now that that's what? 1. So for those two terms together, and it's okay that they're not next to each other, I can combine them and make them 1. And then I still have left plus 1 minus 2 cosine y over 1 minus cosine y times sine y equals 2 cosecant y. 1 plus 1 up there is going to be 2 minus 2 cosine y over 1 minus cosine y times sine y. That equals 2 cosecant y. In the numerator, I have a GCF. So we get 2 times 1 minus cosine y over 1 minus cosine y times sine y equals 2 cosecant y. All right, y'all can go ahead and pack up and go. I'm going to finish this question so it's done, and if you need to go back or we need to talk about it again tomorrow, we can. All right? Cancel those. Y'all have a great day. So that leaves me with 2 over sine y equals 2 cosecant y. And then this is what I get. Sorry that took to the bell. Whew.